Boys and girls, and welcome to another lesson of Technical Sciences Grade 12. You are still with me, Mr. Spiwe Sibanyoni, and we are continuing with work, energy, and power. Now, in the previous days of the week, we dealt with work extensively, as well as energy, as well as power. And we've learned the relationship between all these particular concepts, which is work, energy, and power. And in the previous days, we focused more on energy, which was the gravitational potential energy as well as the kinetic energy. And from that, we were able to learn more about mechanical energy. Now, mechanical energy is very important because it encompasses all these particular concepts together. And as a result, we will be continuing basically revising more of mechanical energy and basically as well trying to understand mechanical energy better. So this will be the outline of the lesson. I will be reminding you again what you need to know, particularly in terms of mechanical energy. You need to remember that as well. In the features of the topic, we will be learning more about mechanical energy and we'll be doing more questions on mechanical energy. And lastly, I will be reminding you again how many marks this topic is going to be for your preparatory examination as well as the end of the year examination, because I'm aware there might be those that have actually started tuning in today. So as per our examination guidelines, remember we use them to prepare for our examination. So what we need to know is that we must be able to state the principle of conservation of mechanical energy. Now, sometimes it is referred to as the law of conservation of mechanical energy. So just know that it is one thing, right? And stated there, we know the total mechanical energy in an isolated system remains constant. Then we also need to remember that a system is isolated when the net external force acting on the system is zero. And we must be able to solve conservation of energy problems using the equation for mechanical energy, and also be able to use that equation to solve problems that involve kinetic energy, potential energy, and velocity in one dimension. So we're only dealing with one dimension, so really not that difficult, right? Just a reminder again, remember you must be able to define the term mechanical energy, and we know is the sum of an object's gravitational potential energy and its kinetic energy. And we also know that to calculate the mechanical energy, you will use that formula there. EM is equal to EP plus EK. Remember the E is for the energy, the M is for mechanical. So that is the symbol for mechanical energy. That is the symbol for gravitational potential energy. And that is the symbol for kinetic energy. And we must be able again to state the law of conservation of mechanical energy, or what we refer to as the principle of conservation of mechanical energy. And we know that the total mechanical energy of an isolated system remains constant. In other words, the total mechanical energy, if the system is isolated, remains unchanged. It is conserved, it doesn't change. And then, if it doesn't change and the system is isolated, it means when you take the mechanical energy at a position that we can refer to as position 1, it must be equal to the mechanical energy at a position that we can refer to as position 2. Why? Because then we assume the system is isolated, and if the system is isolated, then the mechanical energy must be equal it must remain constant at both positions, which in this case we refer to as position 1 and position 2. Furthermore, remember now from our very first topic in the year when we're dealing with Newton's laws of motion, we were supposed to know how to define the term isolated system. And we say an isolated system is a system where the net external force is equal to 0. So remember that. Right. So we dive straight into questions to check our understanding of mechanical energy. Now, here they give us a scenario and they tell us a brick is dropped from a high scaffolding. Now, a scaffolding, we know it is that equipment that the builders use when they are going at a higher level of a particular building. So a brick is being dropped. Now, immediately as a science learner, we know that when they say a brick is dropped, it means from where it is starting, the speed must be 0 meters per second because it is dropped. It is not thrown downwards. So when we drop it, it means it leaves that particular position with a speed of 0 meters per second. Then they say we must ignore air resistance. Immediately when they say we must ignore air resistance, we know that means something to us. It means the system is isolated. It tells us that the system is isolated. So as and when you are reading these questions, I am expecting you to be able to underline these words and write exactly what it means, because that will guide you in understanding the questions that they are going to ask you and being able to answer them. So they tell us what they ask us now, what happens to the brick's energy? Then we are given 4 options here. So they want to know about the kinetic energy, the potential energy, and the mechanical energy. Now, for the mere fact that they said we must ignore air resistance, it tells us that the system is isolated. And if the system is isolated, according to the principle of conservation of mechanical energy, it says the total mechanical energy of an isolated system remains constant. In other words, the mechanical energy of this particular system is never going to change. Everywhere where that object is, everywhere where the brick is, the mechanical energy is going to be the same. It is going to be conserved. Why? Because the system is isolated. So anywhere in the part of the motion, if I calculated the mechanical energy at the top, if it gives me 50 joules, if I calculate the mechanical energy at the bottom, I'm still expecting to get 50 joules. If I calculate the mechanical energy halfway through its motion, I'm still expecting 50 joules because we are ignoring air resistance, so the system is isolated. So under mechanical energy, I am looking for constant. So I can see under A it's constant, under B it's constant. So our answer lies somewhere between A and B. So I am immediately eliminating C and D. Now I go and I check the potential energy. Now remember, the formula for potential energy is EP is equal to mgh. Now we know when we define potential energy, we say it is the energy the object possesses because of its position from the surface of the earth. So our brick is going down. Now, when the brick is going down, it means the height is decreasing. Remember there, my learners, if this is the ground, when the object is falling from the top, right? When it is dropped from the top, as it is being dropped, it goes down. And as it goes down, what is happening to the height? The height keeps on decreasing. Because how do we determine the height? The height is measured from the ground to the position where the object is. So from where it was dropped, that was the maximum height. So from the ground up to where it was, just before it was dropped, is the maximum height. So when we continue to drop, as it continues to go down, and let's say at some point it is here, right? It means the height has decreased because now the height is from there up to there. And according to this formula, if this value, which is the height, keeps on decreasing, then it means the value of the gravitational potential energy is going to decrease. So under gravitational potential energy, I am expecting decreases. So I check potential energy, I get decreases. So decreases, mechanical energy, constant. So these two options are correct. But this one is wrong. This one, it's still correct. Now, in terms of kinetic energy, I know when it was being dropped, from where it was dropped, we agreed that when you drop something, you are not throwing it. So it actually begins with a speed of 0. But when the object goes down, then the speed of the object keeps on increasing up until it hits the ground. Now, according to the formula for kinetic energy, we know kinetic energy is represented by the symbol EK, and it is given by EK is equal to half mv squared. So when it was right on top, the speed was 0. So if we substitute V as a 0 there, it means the kinetic energy is 0. But as it continues to go downwards, the speed increases. So the value of V will be a value that is greater than 0 meters per second. So as it continues to go down, the value keeps on increasing. And when you substitute EK there, then you expect the kinetic energy to be increasing. And therefore, increases also applies. This is also correct. But obviously, the most correct option is then option number B. Because as the object is being dropped, its speed keeps on increasing, and hence the value of EK increases. When the object is being dropped, the height keeps on decreasing because we measure the height from the ground up to where the object is. So I'm expecting the gravitational potential energy to decrease. And then we've been told that the system is isolated. And according to the principle of conservation of mechanical energy, the total mechanical energy of an isolated system remains constant. So it remains unchanged. It remains conserved. And therefore, I'm expecting constant there. Are we together? Right. So the correct answer there is definitely a B. And you know the reasons why your answer is B. So there we go. There's the principle. The total mechanical energy of an isolated system is constant. It remains constant. Right, so that's it on question number 1. Now, let us go to question number 2. Now, here we have a parachutist, and the parachutist falls from a plane, and we must ignore air friction. Now, immediately when we ignore air friction, they ask us which of the following graphs correctly depicts the potential energy of the free-falling jumper relative to his height above the ground? So according to this statement, we are trying to find out the relationship between the potential energy as well as the height. So in this particular diagram, we are given one variable there, which is the potential energy. And on the x-axis, we actually have the height. The same thing applies EP, and there we have the height. Gravitational potential energy. On the y-axis, we have the height. Gravitational potential energy. On the y-axis, we have the height. So we want to know what is the relationship between the potential energy of the free-falling jumper relative to his height. Now, if we go back to our formula again, and I want to just make a simple example for you. EP is equal to mgh. So this formula talks to gravitational potential energy relative to height. Now, let us take for an example the mass of the parachutist. Let us say it was 60 kilograms. So there I would have a 60. Then my gravitational acceleration, we know it's a value that we get on the data sheet. It's a constant. We will multiply by 9,8. And let us say the parachutist comes from a height that is, let's say, 100 meters. Let's say the parachutist is at 100 meters above the ground. If you calculate the gravitational potential energy, you will see that it gives you 58,800 joules, right? Now, let us say we want to check the relationship with height. Now, let us double the height of the parachutist from the ground. And let us say again, EP is equal to mgh. And the mass of the parachutist, it's still 60. The gravitational acceleration, it's still 9,8. But now we double the height, and the height is now 200. Then you will see that the gravitational potential energy is 117,600 joules. Now, according to these calculations, we can actually establish the relationship between gravitational potential energy and height. The mass doesn't change, the gravitational doesn't change, the gravitational acceleration doesn't change, it's the same there. 60 there, 60 there. Gravitational acceleration 9,8, 9,8. But from in the first scenario, the parachutist was 100 meters above the ground. But in the second scenario, the parachutist was 200 meters above the ground. It means he was twice the height from the original one. And we see that the gravitational potential energy then doubles. It means if the gravitational potential, it means if the height doubles, then the gravitational potential energy doubles. When the height increases, the gravitational potential energy increases. Now, for the mere fact that if the height doubles, the gravitational potential energy doubles. That tells me that the relationship is directly proportional. It also tells me that if the height is 0, for example, EP is equal to mgh, the mass is still 60, the g is 9,8, and the height is 0, then I'm expecting the gravitational potential energy to be 0. In other words, where the height is 0, the gravitational potential energy must also be 0. When the height doubles, the gravitational potential energy doubles. So I'm expecting to get a graph that cuts through the origin. Why? Because when the height is 0, the gravitational potential energy is also 0. So it must cut through the origin. And when the height doubles, the gravitational potential energy also doubles. So I'm expecting to get a straight line that cuts through the origin. And that's exactly what direct proportionality means. And therefore, the correct answer there is going to be A. This one is totally out because it doesn't cut through the origin. From this equation, we can see when the height is 0, then the gravitational potential energy must be 0. But here you can check, when the height is 0, the gravitational potential energy is greater than 0, so that is incorrect. The same applies there. When the height is 0, the gravitational potential energy is greater than 0. It is incorrect. It does not agree with the formula. This one, true, it cuts through the origin. When the height is 0, the gravitational potential energy is 0. But now this relationship is not direct proportionality, and hence this one also becomes wrong. And the only correct answer is A. Right. Let us just erase there. Right. Then the next question says, how will we know whether the mechanical energy of a girl moving down a slide is conserved? Now, if we say something is conserved, what does that mean? It means the mechanical energy is not changing. That's what conserved means. Something does not change, it remains constant. So if something remains constant, her kinetic energy at the top must be equal to her potential energy at the bottom of the slide. That is the first option. Her kinetic energy at the bottom must be equal to her potential energy at the top of the slide. Her kinetic energy at the bottom must be equal to her mechanical energy at the bottom. This one we can see is completely wrong because mechanical energy can never be equated to kinetic energy. It can be equated to the sum of the gravitational potential energy and the kinetic energy. And option D says her mechanical energy at the top must be equal to her mechanical energy at the bottom. Now that is true. That is correct. If the mechanical energy at the top is equal to the mechanical energy at the bottom, then we know that the mechanical energy is conserved. So the most correct answer there is option number T. Right. Now, let us look at contextual questions. These are structured questions. Now, the question reads as follows. A vase is dropped. My dear learners, I have taught you over and over again that these words have a meaning for us. Because if you don't take note of this, when you go to the questions, you will start thinking that you were not given enough information. But actually, by just saying a vase is dropped, then they are telling me that the speed from where it is dropped is initially 0 meters per second. From the balcony of a flat, the height of the balcony above the ground is 20 meters. And the mass of the vase is 2 kilograms altogether. Then we are required to calculate the vase's potential energy before it starts to fall. Now, what you normally do is draw for yourself a diagram. So let us say this is the top of the balcony, and then the vase is being dropped, right? We hope that it's not an expensive vase. And then the vase will eventually hit the ground. So we can actually take what they have given us and we can put it into a diagram. So a vase was dropped. So at the top there already, I know that the value of V is equal to 0. The height of the balcony above the ground is 20 meters. So from this point, okay, just do it like this. Right, 20 meters. Can you see how you can put this in a diagram? So it's 20 meters from the top of the balcony to the ground. And we know that the mass is definitely 2 kilograms. And they tell us to ignore air resistance. Again, what are they telling me? They are telling me that the system is isolated. 1.1, we need to calculate the vase's potential energy before it starts to fall. So we start. We want the potential energy, and we know very well that is the gravitational potential energy. We go straight to our formula sheet. We get the formula for gravitational potential energy, EP is equal to mgh. There we allocate you 1 mark. Then the mass 2, and it's already in kilograms, so I don't need to convert. I put a 2. Gravitational acceleration 9.8. The height just before it started to fall from here to the ground, it was 20. The entire substitution being correct, we get a mark. You do your mathematics, you get that this gives you 392. The final mark there, my learners, is for the correct magnitude of the gravitational potential energy as well as the correct unit. Are we together? Right. In question 1.2, they tell us its kinetic energy as it reaches the ground, or we need to calculate its kinetic energy as it reaches the ground. And honestly speaking, we don't need to be able to calculate that kinetic energy. We actually know that the kinetic energy is going to be 392 joules. Why? Because the potential energy there, we calculated it, and we found that it gives us 392 joules. Now, when we get to this point, the object doesn't have a height, so the potential energy is 0. So we ask ourselves, what happened to that original potential energy that it had? Now, we know all of that potential energy was transformed into kinetic energy. So we expect the EK to then be equal to 392 joules. And we've actually talked about this, my dear learners, over the past 2 days. So the object there, because of the height, it has a potential energy of 392, but a kinetic energy of 0 joules because the speed was 0. But as it goes down, the height keeps on decreasing, so the potential energy decreases because it is being converted into kinetic energy. So when it gets to the ground where the height is completely 0, then it means all of that potential energy has been completely converted into kinetic energy. And we know that is going to be the case because the system is isolated. There we get a mark. Then they say we need to get the speed at which the vase reaches the ground. So we want to know the speed as it goes down. What is the speed with which it hits the ground? And it's a very easy calculation. We'll say kinetic energy is equal to half mv squared. Now, we know the kinetic energy on the ground is 392. That substitution alone will carry 1 mark, is equal to half multiplied by the mass is 2 kilograms multiplied by v squared. Now, my dear learners, this is a mistake that you always make, most of you. Remember, 392 will be equal to half times 2 times v squared. So when you take half multiplied by 2, it gives you 1. You multiply by v squared, it gives you v squared. In other words, v squared is actually equal to 392 meters per second. But you are not solving for v squared, you are solving for v. So to solve for v, you must take the square root on both sides. And if you take the square root of 392, it will then give you 19.8 meters per second. Are we together? And we still could have used that principle there, the mechanical energy at the top is equal to the mechanical energy at the bottom. Even if you use that, you will still get the most correct answer. You will get exactly 19.8 meters per second. So we'll let you explore that one. Right. In another question, Danielle climbs on a chair and lifts her teddy of mass 0.4 kilograms. So the mass is already in kilograms. I know if I have to use it, I don't need to do any conversions. Up to height h above the ground. She drops immediately. When we say drops, we know that the speed is definitely equal to 0. From this height and its speed as it hits the ground is 2.5 meters per second. Then we are required to ignore air friction, means the system is isolated. And here I'm just asking you simple questions. What type of energy did Teddy gain when it was lifted to a height h? Obviously, when you increase h, what increases? The gravitational potential energy, because it is given by the formula EP is equal to mgh. Now, what was I testing actually here? Some of the learners would actually get a 0 here because they would just say potential energy. Remember, we have different types of potential energies, chemical potential energy, and so on. So in this case, it is gravitational potential energy. So that word gravitational is the keyword. And we are asked, what is the magnitude of the acceleration of the teddy when it starts to fall? Obviously, it's a free fall. So the acceleration is the acceleration due to gravity, and the value will be 9.8 meters per second squared. Right. Now we are required to calculate the teddy's kinetic energy just before it reaches the ground. It's a simple calculation, my dear learners. We know the formula for kinetic energy and we get it from the formula sheet. So EK is equal to half mv squared. Are we together? Then remember, we were told that as it hits the ground, the speed is 2.5 meters per second. So EK is half mv squared, half multiplied by the mass, which is 0.4, multiplied by the speed just before it hits the ground, which was 2.5. But what am I trying to teach you here again, my dear learners, is that the squared only applies to the speed. It doesn't apply to the entire thing. So it's half 0.4 multiplied by 2.5 squared, and you get a value of 1.25 joules. And remember, I said again, a joule is a capital letter J. Then we are required to calculate the height from which the teddy was dropped. Very easy calculation as well, my dear learners. We've been told that the system is isolated. Are we together? Right. So if the system is isolated, mechanical energy at the top will be equal to the mechanical energy at the bottom. So any of those equations is going to carry a mark. That is for anyone. So this is exactly how we will mark you. For any one of those, it will carry 1 mark. Then at the top, okay, the mechanical energy, we know it is the sum of the gravitational potential energy and the kinetic energy. So this side is for the top, and we'll still do the gravitational potential energy and the kinetic energy, but this is going to be at the bottom. Then the gravitational potential energy is given by the formula mgh. The kinetic energy is given by the formula half mv squared. But remember here, I'm still working with the top. And I will still break it down the same way for the bottom. Now I'm ready to substitute. At the top, the mass was still 0.4. The gravitational acceleration was 9.8. The height was given as h. We were not given the value of the height, so I will substitute it as h. Plus, remember, I'm still working with the top. At the top, the kinetic energy is given by half, multiplied by the mass, which is 0.4, multiplied by the speed at the top is 0. How do we know it's 0? Because they said it is being dropped. So it will be 0 squared. This will be equal to, now we go to the bottom. When we go to the bottom, the mass is 0. The gravitational acceleration is 9.8. The height is 0 because we are taking the bottom to be the ground. Plus half multiplied by the mass is 0.4, and just before it hits the ground, or as it hits the ground, the speed was 2.5 squared. And you can see the only variable left for us there to solve for is h. So you do your mathematics and you will see that h will give you 0.32 meters. So how do we mark this one? If we are very lenient with the marks, we'll give you a mark there, 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 and we'll give you a mark there. So there, it's actually a 6 out of 6 marks. Right. Now we move to the last question for the day. It reads as follows. Michael and his skateboard together have a mass of 60 kilograms. You see, I'm indicating the 60 kilograms there for you, because when we substitute into formulas, we definitely have to make sure, my dear learners, that we substitute values that are already in SI units. Now, he skates past point A, there's point A, at a speed of 7 meters per second. And they tell us the surface is frictionless. Immediately when they say the surface is frictionless, we know in science, it means they are telling us to take the system to be isolated. Altogether, it means somewhere, somehow, if I thought an answer, I could get it using the principle of conservation of mechanical energy, I definitely know that I can use it. How do I know I can use it? Because definitely the system is isolated. 1.1, you are required to state the principle of conservation of mechanical energy in words. And I indicated the words for you because you need to state it in words. Some of the learners will give it in formula and say mechanical energy at point A is equal to the mechanical energy at point B. So that is incorrect. So a nice principle there. I'm giving you 1 minute to think about it. See if you can remember it from the top of your head because it's a recall question. And after 1 minute, when I start to state it, you do the same with me and we state it together. Your 1 minute starts now. Right? Your 1 minute is over. So we state it together. And I'm watching you, by the way. Right? It states the total mechanical energy of an isolated system remains constant. Others are probably saying the total mechanical energy of an isolated system remains conserved. Right. Question 1.2. We are required to calculate Michael and his skateboard kinetic energy at point A. Now we want kinetic energy, so we'll use the formula for kinetic energy. Right. So kinetic energy is given by half mv squared. We get the formula from the formula sheet, and then half multiplied by the mass, which was 60, and the speed at 0.8 was 7. We get a mark, and then we get a total of 1,470 joules altogether. Right. Then what is Michael and his skateboard mechanical energy at point B? Right? This is actually at point B. This is actually at point B. We need to know what is Michael's and his skateboard mechanical energy at point B. So we find that Michael there had a kinetic energy of 1470. Okay, let me fix that. Right, we get the pen. There we go. 1470. I'm sure you're probably saying our teacher's handwriting is so beautiful. Right, 1470 joules. So if I asked you what is the potential energy there, you will say to me, say, the height is 0 there, so the potential energy is 0. If I said what is the mechanical energy, you would say at that point, mechanical energy is EP plus, rather it's EP plus EK, so the mechanical energy is 1470 joules. You will remember that because mechanical energy is the sum of the gravitational potential energy and the kinetic energy of an object. So that gives you 1470. So what will be the mechanical energy when he is now at point B? And you're going to say to me, Menier, I'm still expecting the mechanical energy at that point to be 1470 joules. Why? Why is the mechanical energy the same between point A and point B, which are different parts? Because the system is isolated and the mechanical energy remains constant. Right. So you enjoyed that question. 1.4, which principle will you use to calculate the speed at B? So which principle would you use to calculate the speed at B? And the learner is probably saying, Menier, it will be the principle of conservation of mechanical energy. It will be the principle of conservation of mechanical energy. Then we are asked, will Michael reach height B on his skateboard? Show your calculations. So we want to know if he is going to reach that height, which is point E. Now my head is telling me now, I must actually calculate the height that he's going to reach at the top. And I must use the principle of conservation of mechanical energy to actually determine the maximum height that he can reach. And if I find that the maximum height he can reach is, say, 1.5 meters, then I will say, no, he won't reach point B. If I see that it's 2 meters, I know he will reach point B. If it's greater than 2 meters, he will reach point B. So I need to perform that calculation. And the calculation there to actually determine whether he will reach B, it means I must definitely check the height that he is going to reach. Right? There we go. So the mechanical energy at point A is equal to the mechanical energy at point B. Then I get the potential energy to be mgh, the kinetic energy to be half mv squared, and I will do the same for both the other side, which is point B. Then at A, the mass is 60, the g is 9.8, the height is 0. Plus half, the mass is 60, the speed at A was 7 meters per second, then I square it. Then at B, the mass is 60, the g is 9.8, and the height is 2. Plus, because it was 2 meters, plus half multiplied by the mass, which is 60 times v squared. And I can see that the value for v is 3.13 meters per second. What does that mean? It means definitely at point B, Michael has a speed, and the speed is 3.13. So it definitely tells me that he is going to reach that particular point. altogether. Right. Then, assuming that he can reach B, calculate the speed at C. Now, here we can answer this question in two ways. I can say the mechanical energy at point A is equal to the mechanical energy at point C. Or I can say the mechanical energy at point B is equal to the mechanical energy at point C, because mechanical energy is conserved. So either way, whether you say mechanical energy at A is equal to the mechanical energy at C, or you say the mechanical energy at B is equal to the mechanical energy at C, you will end up with the same answer in terms of the speed at C. Simple calculation as well, my dear learners. We can definitely use that principle of conservation of mechanical energy. Why? Because mechanical energy is conserved. And there it is. Mechanical energy at A is equal to mechanical energy at C, because it's the sum of the gravitational potential energy and the kinetic energy. Then we break it down again. Potential energy mgh, kinetic energy half mv squared. This is for point A, and I will do the same for point C. Then at point A, the mass is 60, g is 9.8, height is 0 because he was right on the ground, plus half the mass multiplied by the mass, which is 60, multiplied by the speed, which is 7 meters per second, squared is equal to, at C, the mass is 60, the G is 9.8, but remember the height above the ground from point C, it was 0.8 meters. So we'll put 0.8 plus half times the mass, which is 60, times V squared, which is what I do not know. You do your mathematics. After you get V squared, you take the square root, and you will see that V gives you 5.77 meters per second. So remember, we knew the height there to be 0.88, and we were required to get the value for V. And hence we said the mechanical energy at this point must be equal to the mechanical energy at that point. You get the EP plus EK at this point is equal to EP plus EK at that point. You do your substitution, V is the only one that is left. And then we find our V to be 5.77 meters per second. So your homework for today is to go and do the same calculation, but don't equate mechanical energy at A with mechanical energy at C. That's the one that we did. You then equate the mechanical energy at B with the mechanical energy at C, and you will get the same answer for the speed at C. But remember now, for you to be able to do that, you need to use this value that we calculated in 1.4. Right. Lastly, my dear learners, from me, and if you've just joined us, remember work, energy, and power is going to be plus minus 22 marks. You are probably going to get about 6 marks in your multiple choice questions, and you will get about, rather 4 marks in your multiple choice questions and about 18 marks in your long and structured questions. I hope you enjoyed the lesson for today. I definitely did, and I'm going to see you tomorrow. So please do my homework. Thank you very much for tuning in, and I will see you tomorrow. Thank you very much.